A well under the house can serve as an effective grounding electrode if certain conditions are met. According to the National Electrical Code or NEC, a metal well casing can be used as a grounding electrode if firstly, it is at least 10 feet long and buried below permanent moisture level, secondly, it is in direct contact with the earth, and thirdly, it is not coated with a non-conductive material. There are several advantages of using a well as a grounding electrode. Firstly, low impedance. Well casings provide a low resistance path to the earth. Secondly, convenience. It is readily available and does not require additional installation or excavation. The NEC does not specifically require the use of a well as a grounding electrode if it is present. However, if it is used, it must meet the following additional requirements. The well casing must be connected to the electrical system with a copper or copper-clad grounding electrode conductor. A supplementary grounding electrode, such as a ground rod or buried metal plate, may also be required in some cases. If a well is present and meets the NEC requirements, it can be utilized as an effective grounding electrode. While not mandatory, its use can simplify and improve the grounding system. However, it is always recommended to consult a qualified electrician to determine the specific requirements and ensure proper installation. Grounding electrodes are a critical component of electrical safety. They provide a low impedance path for fault current to return to the source, which helps to trip a circuit breaker or fuse and energize the circuit. This protects people from electric shock and reduces the risk of fire. There are several types of grounding electrodes, including ground rods, ground plates, metal underground water pipes, and building steel. The type of grounding electrode that is used will depend on the specific site conditions and the requirements of the National Electrical Code. Ground rods are the most common type of grounding electrode. They are typically made of copper or copper-clad steel and are driven into the ground. The length and diameter of the ground rod will depend on the soil resistivity. Ground plates are typically made of copper or steel and are buried in the ground. They are often used in areas where the soil resistivity is high. Metal underground water pipes can be used as grounding electrodes if they meet certain requirements. The pipe must be electrically continuous and must be in direct contact with the earth for at least 10 feet. Building steel can be used as a grounding electrode if it meets certain requirements. The steel must be electrically continuous and must be in direct contact with the earth. The National Electrical Code or NEC provides detailed requirements for grounding electrodes. These requirements are designed to ensure that the grounding electrode is effective and safe. The NEC also requires that the grounding electrode system be tested periodically to ensure that it is still effective. A qualified electrician should be consulted to install and test the grounding electrode system. The grounding electrode conductor or GC is used to connect the grounding electrode to the electrical system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The grounding electrode conductor must be made of copper or aluminum. It must be protected from physical damage. The grounding electrode conductor must be connected to the grounding electrode with a listed connector. The grounding electrode system must be installed in accordance with the National Electrical Code. The grounding electrode system must be tested periodically to ensure that it is still effective. A qualified electrician should be consulted to install and test the grounding electrode system. Proper grounding is essential for electrical safety. It protects people from electric shock and reduces the risk of fire. It is important to have a qualified electrician install and test the grounding system. Grounding is a critical safety measure in electrical systems. It provides a path for fault current to flow back to the source, tripping a breaker or fuse to energize the circuit. This protects individuals from electric shock and minimizes the risk of fire. Grounding electrodes are essential components of a grounding system, providing a connection to the earth. The National Electrical Code or NEC outlines requirements for acceptable grounding electrodes. These may include ground rods, ground plates, metal underground water pipes, and building steel. When considering a well casing as a grounding electrode, it's crucial to adhere to the NEC guidelines. The casing must be metallic, at least 10 feet in length and buried below the permanent moisture level. Direct contact with the earth is necessary, and the casing should not be coated with any non-conductive material. Connecting the well casing to the electrical system requires a grounding electrode conductor, typically made of copper or copper-clad steel. The conductor must be appropriately sized based on the service entrance conductors. A listed connector must be used to ensure a secure and reliable connection. In some situations, a supplementary grounding electrode, such as a ground rod or ground plate, might be necessary in addition to the well casing. This is determined by factors like soil resistivity and local electrical codes. Soil resistivity is a measure of how well the soil conducts electricity. High soil resistivity can hinder the effectiveness of a grounding electrode. A qualified electrician can assess soil resistivity and determine the appropriate grounding solution. Regular inspection and testing of the grounding system are vital to ensure its continued effectiveness. This includes verifying the integrity of the grounding electrode conductor and the connections to the grounding electrode. The National Electrical Code specifies testing requirements for grounding systems. Consulting with a licensed electrician is essential for proper installation, inspection, and maintenance of the grounding system. They can ensure that the system meets all applicable codes and standards, providing a safe and reliable electrical installation. Improper grounding can have serious consequences, including electric shock, fire hazards, and damage to electrical equipment. A properly installed and maintained grounding system is a critical investment in safety and protection. Understanding the principles of grounding and the requirements of the National Electrical Code is essential for anyone working with electrical systems. Continued education and training are important to stay up to date with the latest codes and best practices. Grounding is a fundamental aspect of electrical safety, and it should never be overlooked. A well-designed and properly installed grounding system is essential for protecting people and property from the hazards of electricity. In addition to the physical components of a grounding system, it's also important to understand the concepts of bonding and equipotential planes. Bonding refers to the practice of connecting all metallic parts of an electrical system together to create a low impedance path for fault current. This helps to ensure that all metallic parts are at the same potential, reducing the risk of electric shock. Equipotential planes are created by bonding together all metallic objects in a specific area, such as a bathroom or swimming pool area. This helps to minimize the voltage difference between different objects, reducing the risk of electric shock. The National Electrical Code provides detailed requirements for bonding and equipotential planes. It's important to follow these requirements carefully to ensure a safe electrical installation. A qualified electrician can provide guidance on proper bonding and equipotential plane techniques. Grounding and bonding are often used together to create a comprehensive electrical safety system. Grounding provides a path for fault current to flow back to the source, while bonding helps to minimize voltage differences between different objects. Together, these measures provide a high level of protection against electric shock and fire hazards. Electrical safety is a shared responsibility. Everyone who works with or around electricity should be aware of the potential hazards and take steps to protect themselves. This includes following safe work practices, using appropriate personal protective equipment, and being aware of the location of grounding and bonding connections. Education and training are essential for promoting electrical safety. By understanding the principles of electricity and the requirements of the National Electrical Code, individuals can work safely and prevent accident. Grounding is a critical aspect of electrical safety that should never be taken for granted. A properly designed, installed, and maintained grounding system is essential for protecting people and property from the hazards of electricity. Always consult with a qualified electrician for any electrical work, including grounding and bonding. They can ensure that the work is done safely and in accordance with all applicable codes and standards. Furthermore, it is important to understand the role of surge protection in conjunction with grounding. While grounding provides a path for fault currents, surge protection devices or SPD protect against transient voltage surges, such as those caused by lightning strikes or switching events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. SPD should be installed at the service entrance and at various points throughout the electrical system to provide comprehensive surge protection. The effectiveness of SPD depends on a good grounding system. A low-impedance grounding path allows the surge current to be safely dissipated. Therefore, it's important to ensure that the grounding system is properly installed and maintained when using SPD. The National Electrical Code provides requirements for the installation of SPD. These requirements include proper grounding and bonding of the SPD. A qualified electrician can ensure that SPD are installed correctly and that they are properly integrated with the grounding system. Surge protection is an important complement to grounding in protecting electrical systems from damage. By combining grounding and surge protection, a comprehensive electrical safety system can be achieved. Electrical codes and standards are constantly evolving to address new technologies and safety concerns. It's important to stay up to date with the latest codes and standards to ensure that electrical systems are installed and maintained safely. The National Electrical Code is updated every 3 years. It's essential to use the latest edition of the NEC when designing and installing electrical systems. Local electrical codes may also have additional requirements that must be followed. A qualified electrician can provide guidance on the latest codes and standards and ensure that electrical work is done in compliance with all applicable regulations. Continuous learning and professional development are essential for staying current with the ever-changing landscape of electrical safety. By investing in education and training, individuals can enhance their knowledge and skills and contribute to a safer electrical environment. Grounding is not just a theoretical concept. It's a practical application of electrical principles that has a direct impact on safety and reliability. By understanding the importance of grounding and following the requirements of the National Electrical Code, individuals can help to prevent electrical accidents and protect themselves and others from harm. Electrical safety is a shared responsibility that requires the cooperation of everyone involved in the design, installation, and maintenance of electrical systems. By working together, we can create a safer and more reliable electrical environment for all. A well can certainly function as a grounding electrode, but it's crucial to understand the specific requirements and considerations involved. Firstly, the National Electrical Code or NEC sets the standards for grounding electrodes, including those utilizing metal well casings. To be compliant, the well casing must be metallic, possess a minimum length of 10 feet buried below the permanent moisture level, maintain direct contact with the earth, and remain free from any non-conductive coatings. Secondly, connecting the well casing to your electrical system demands a grounding electrode conductor typically crafted from copper or copper-clad steel. Sizing this conductor correctly based on your service entrance conductors is paramount. Furthermore, a listed connector must be employed to ensure a secure and reliable connection. Thirdly, while a well can be an effective grounding electrode, supplemental grounding electrodes, such as ground rods or ground plates, might be necessary depending on local soil conditions and code requirements. Soil resistivity plays a significant role in determining the effectiveness of a grounding electrode. A qualified electrician can assess the soil resistivity to your location and advise on the necessity of supplementary electrodes. Fourthly, regular inspection and testing of your grounding system are essential to guarantee its continued effectiveness. This includes verifying the integrity of the grounding electrode conductor and the connections to the well casing. The NEC mandates periodic testing of grounding systems to ensure they meet safety standards. Fifthly, consulting with a licensed electrician is highly recommended for any grounding system work. They possess the expertise to ensure proper installation, inspection, and maintenance, guaranteeing that your system adheres to all relevant codes and standards, thereby ensuring a safe and reliable electrical setup. Sixthly, understanding the broader context of grounding within your electrical system is vital. Grounding works in conjunction with bonding, which involves connecting all metallic parts of your electrical system to create a low impedance path for fault currents. This helps maintain equipotentiality and reduces the risk of electric shock. Seventhly, grounding also plays a crucial role in surge protection. Surge protection devices, or SPD, divert transient voltage surges, such as those caused by lightning strikes, to ground, preventing damage to sensitive electronic equipment. SPD rely on a robust grounding system to effectively dissipate surge currents. Eighthly, improper grounding can lead to serious consequences, including electric shock, fire hazards, and damage to electrical equipment. Therefore, adhering to the NEC guidelines and seeking professional assistance are paramount to ensure a safe electrical environment. Ninthly, it's important to remember that electrical codes and standards are constantly evolving. Staying up to date with the latest revisions is crucial to ensure compliance and maintain safety. The NEC is updated every 3 years, reflecting advancements in technology and safety practices. Tenthly, grounding is not merely a theoretical concept, it's a practical application of electrical principles that has a direct impact on safety and reliability. By understanding the importance of grounding and following the relevant codes and standards, you contribute to creating a safer electrical environment for yourself and others. Finally, electrical safety is a shared responsibility that requires the cooperation of everyone involved in the design, installation, and maintenance of electrical systems. By working together and prioritizing safety, we can minimize the risks associated with electricity.